In Unit 3, Homework 6, we're going to be combining everything that we've learned about exponents and logs into solving exponential and logarithmic equations. Now before we do that, we need to cover a few properties of logs. So some of these we've already looked at in our last lecture, but let's go ahead and expand on those just a little bit. I'm going to abbreviate these a little bit. Remember, these would work for common logs, natural logs, logs of any base. So if we have the log base b of a product, and the product would be m times n, and notice both of these are in parentheses, I could rewrite this as the sum of the logs. Log base b of m plus log base b of n. Okay, so the log of the product is the sum of the logs, is how we'd want to remember this. Now, this works with numbers as well, so let's go ahead and make up some numbers here. Let's look at log base, let's say 4 of 2 times 3. That should be equivalent to log base 4 of 2 plus log base 4 of 3. So let's go ahead and grab our calculators and see if that works. Now remember, if you have the log base key, you can use that. So I'm going to use my log base key, and I'll also show you the conversion as well. So what did we decide? Log base 4 of 2 times 3, I believe it was. So log base 4 of 2 times 3. Okay, so we said that's equivalent to log base 4. So I'm going to say log base 4 of 2 plus log base 4 of 3. So you can see that these are equivalent. Sometimes it's a lot easier for me to work with the sum than it is the difference. And when we're trying to solve these equations, it definitely will work a little bit easier if I can combine a sum into a product or vice versa. So this is if I have the log base key. How do I do these problems if I don't have the log base key? Well, remember, this would be the same. I'd still be trying to find log base 4 of 2 times 3. That's still the problem. And I'm still going to rewrite this as log base 4 of 2 and log base 4 of 3. But the difference is when I plug this into my calculator, I will rewrite this as the log of 2 times 3. And remember, 4 is my base. Base goes on the bottom, over log of 4. This is the common log. I can replace this with natural log and I'll get the exact same answer. This would be log of 2 over log of 4. And this would be the log of 3 over log of 4. Notice base always goes on the bottom. So let's go ahead and plug these into the calculator as well. Do the left-hand side first. Log of 2 times 3 over log of 4. And again, if you want to use natural log, you can. Log of 2 times 3 over log of 4. Okay, so I said that that was the log of 2 divided by the log of 4 plus the log of 3 divided by the log of 4. Make sure you close those parentheses after the argument of the log function. And I still get the exact same value. So using that log conversion, if you don't have a log base key, is going to be invaluable for checking a lot of these answers. So it's a good habit to get into. So what we did for the second part is the same exact problem, but if you don't have that log base key, I could use the log conversion form. So this is using log conversion. And all we did is verify the identity. We didn't solve or anything. I just showed that the identity actually works for numbers. Okay, so let's go ahead and look at another example. Let's look at log base b of not m times n, but let's do m divided by n. The log of a quotient is the difference of the logs. Log base b of m minus log base b of n. And you could go and establish this with numbers just like we did on the last problem if you wanted. Okay, so the quotient of the logs is the difference of the log of the quotient is the difference of the logs. If I had log base b of m to the p, let's say, remember we've looked at this before, I can pull that p out front and just be left with log base b of m. So we've looked at the log of a product is the sum of the logs. We've looked at the log of a quotient as the difference of the logs. And we've looked at where I have an exponent on the argument of the log, I can pull that exponent out front. So these are going to be some of the important properties that we look at. Now, one other property that we've already looked at, that was basically talking about the change of base formula. Now we'll write it down one more time. We just used it up above when we were using or establishing the log of a product. Remember, with the change of base formula, if I have log base b of m, we used this in the last unit as well, this is going to convert very nicely to log base a of m over log base a of b. B is our base goes on the bottom. Now when we looked at this before, we didn't say the a here. Well, it could be any log. This could be log base 2, this could be log base 4, log base 7. What we like to do is we like to convert this to the common log because we have a nice calculator key for that and it's a lot easier to work with. So remember, log base 10 just means common log. So this is log of m over the log of b. I could also use log base e, and that would be the natural log over the natural log of b. b is the base, so base goes on the bottom. So this is the general change to base. I can change it to any base, but the bases we like to change to are the log base 10 and log base e, which are the common and the natural log. So what we're going to be doing is we're going to be working through quite a few simplifications of these problems. Now remember, a lot of these you can check on your calculators either using your log base key if you have it, or using your log conversions if you don't have it. So let's go ahead and look at converting this or rewriting this using the properties of logs. So we want to rewrite this as much as possible. This is the log of a product. The log of a product is the sum of the logs. Now the log base 2 of x I can't really do anything else with. Now for here, I can look at log base 2 of 4, and I know that there's something going on with a 2 and a 4. 2 to the second power is 4, so this simplifies to 2. So this actually equals 2 plus log base 2 of x. Now this means 2 to the second equals 4. Now if you weren't sure about that, you could check this with log of 4 over log of 2 on your calculators. Now remember, I can't cancel the 2 into the 4. I have to take the entire numerator over the entire denominator. So whenever you have just constants running around like we do on this part, you want to make sure that you can't simplify that an extra step. And a lot of times you can do that just by plugging into your calculator. Let's go ahead and look at another one. Let's look at, this one's a little bit confusing, log base t of x to the third. Okay, so I have a base of my log, I have a base of my exponent, and I have my exponent. Now remember, the 3 can pop out front, and I'm going to put 3 log base t of x. So 3 log base t of x. So you can rewrite a lot of these. Now this homework set is pretty long, but I think it's 40-some questions, but most of them are pretty quick little questions like these. Let's look at log base 3 of 27 over y. This is a quotient. The log of a quotient is the difference of the logs. Okay, now log base 3 of y I can't do anything else with. But log base 3 of 27 says 3 to what power is 27? And the answer to the 3 to the what power is 27 is 3, so this is my answer. 3 cubed is 27. Now if you weren't sure about that, you would just take log of 27 divided by log of 3. And remember, the 3 does not cancel into the 27. You just need to simplify that expression. Now a lot of times you'll be given kind of an ugly looking log problem where it's just really complicated. There's lots of layers to it. And then you'll be asked to simplify it completely. So let's go ahead and look at this log base 4 of 64 over the square root of x plus 8. So what I have here is a quotient. So the log of a quotient is the difference of the logs. Now one thing that we want to remember here, and I'll show you another way to look at this as well. 64, okay, 4 times 4 is 16, 16 times 4 is 64. So I could rewrite that as 4 cubed if I wanted. And again, you can simplify that by working with your calculator. The square root of x plus 8 means the quantity x plus 8 to the 1/2. And then what I can do is I can pop the 1/2 out front, I can pop the 3 out front, And I'll be left with 3 log base 4 of 4 minus 1/2 log base 4 of x plus 8. Now, log base 4 of 4 is just 1. So basically what I end up with here is 3 minus 1/2 log base 4 of x plus 8. Okay? Now if you weren't sure how we got this 3, another thing that you could think about is this log base 4 of 64. That's just equal to the log of 64 over the log of 4 using your conversion formula, and I would get 3 out of that. So that's where that 3 comes from as well. So there's a lot of different ways to look at these problems and when you're simplifying them. Now when you're simplifying and you're going through, make sure you double check whether you're working with a product. A product rewrites as a sum of logs, a quotient rewrites as a difference of logs. Sometimes you'll be given the simplified form, let's say like log 4x plus 1 minus log of x, and I have to rewrite this in its original form. Well, this is a difference, so it must have come from a quotient. So this is a log of 4x plus 1 over x. Now there's no simplifying that needs to occur there. That's already ready to go. Let's look at another one. Let's look at 2 ln of x. And again, a lot of your problems you won't see parentheses around the arguments of the functions. I just think it's a good idea to clarify what is the argument of the log. So just like we could pop the 2 out front, I can pop it back up top. Same with the 1/7. So this would rewrite as the natural log of x squared minus the natural log of y to the 1/7. Okay, now so this is a difference. A difference of logs rewrites as the quotient. So this is a natural log of x squared over y to the 1/7, which is the 7th root of y. So again, another rewrite. You always want to rewrite these completely. You already know how to do a lot of the common log conversions that you'll run into, but one that may not be as familiar would be throwing in a constant. So for instance, you might have something like log base pi of 43. Well, log conversions say that's the log of 43 over the log of the base, but in this case that base is pi. So let's look at the log of 43 over the log of pi. And if you wanted to, you could use natural log of 2, natural log instead of log. Log of 43 over log of pi. Pi is up here above the exponent key. And it has specific directions about rounding, so we want to make sure we follow those. Okay, so the log of 43 over log of pi, and directions say round to 5 decimal places is needed. So 1, 2, 3, 4, 5. So this is the spot I want to round to. So this 6 will round this up to a 7. So I'll have 3 point. Oh, wait, I think our final answer says 4 places. So I'm sorry. I read that incorrectly. Round to 4 places. I think on here it says round your intermediate calculations to 5, but we don't need to worry about intermediate calculations because we're using our calculator. So 4 places, 1, 2, 3, 4. So it says to round to 4 places. So it would seem that this 6 would round this to a 7, so I'd have 3.2857. However, the directions on this one are a little strange. It says round all intermediate values to 5 decimal places. So let's figure out what's going on here. Let's look at log of 43. I don't want you to run across this one and get into trouble with it. So this is log of 43, and then we also have the log of pi. So let's take these two numbers and we're going to round our intermediate values to 5 places, and then we'll try and figure out our solution from there. And again, I think what we have for a solution is great, but in order for us to get along with my math lab on this one, we're going to have to make sure we follow their directions. Okay, so if we round this one to 5 places, that would be 1.6334. So 6334. This is my 5th place. The 8 would round this to a 7. This is my numerator. Now my denominator is 4971. 1, 2, 3, 4. And then this 4 would be my 5th place, but the 9 would round it to a 5. Now let's divide these out. 1.63347. So 1.63347 divided by 0.49715. Okay, it looks like we get the same answer either way, or really close to it. Now, one of the reasons I jumped through this little bit of a hoop here is you have to be careful about how you double check this. Now, if we round to 4 places, 1, 2, 3, 4, this is still going to round to a 7. But in your homework problem, if you run into troubles with this, break it out into the two numerator and denominator rounded, and then work from there to make sure that you agree with the answer, because these are going to be a little bit tricky. So for here, whoops, so for here I get the same answer, 3.2857. Now we're going to get into solving equations now, and that's kind of some fun stuff. But what we want to do is we want to remember, if we're solving an equation and I have each side of the equation with the exact same base, what I can do is drop the bases and overall just take the exponents and equate them. So in this particular case, m would equal n then. And it's something important to remember. Now this isn't just magic. What actually ends up happening here is I take the natural log of both sides. So I have the natural log of b to the m equals natural log of b to the n. Now remember, with these exponents I can pull them out front. So I'd have m natural log b equals n natural log b. And then we could divide both sides through by natural log of b. They cancel. ln of b over ln of b is 1 on each side, and I get m equals n. So you can go through and establish this way, and we're going to be using logs to solve, but you can also just realize when the bases are the same, I can just equate the exponents. So let's go ahead and run through solving some of these equations in log and exponential form. Now graphing is going to be invaluable here, so we also want to make sure that we can graph these expressions. Okay, so one of our ideas will always be solving for x. So if we have x times the ln of 9 equals the ln of 28, and I want to solve for x. Well, what's in the way of x being by itself is this ln of 9. So I'll go and divide both sides through by the ln of 9. ln of 9 over ln of 9 is 1, so I get x equal to ln of 28 over the ln of 9. And this is called my exact answer. Okay, so I don't need to come up with a decimal approximation. This is called my exact answer. So we're going to be using the idea of solving for x, equating variables, taking the natural log of both sides to solve these equations. Let's go ahead and look at e to the 0.5x equals 5. Now to solve this equation, what I want to do is to take the ln of both sides. I want to take ln because my base is e. Now if my base was 10, I'd want to take the log. So this is ln of e to the 0.5x equals the ln of 5. And again, whatever you do to one side, you do to the other. Now the whole reason we take the ln of both sides is so I can pop that 0.5x out front. And so now my variable that was in the exponent is now up front, and I'm left with the ln of e. Let me rewrite that. So I have 0.5x times the ln of e equals the ln of 5. But we know that the ln of e is 1. The natural log of e is 1. And if you're not sure about this, you can check it on your calculator. But remember, this is log base e of e. E to the what power is e, and the answer to that is 1. So the natural log of e is 1. That's going to come in handy a lot. So I have 0.5x equals the ln of 5. And then from here, I can solve for x by dividing both sides through by 0.5. However, some of the problems in my math lab ask you to stop at this point. So make sure you read the directions to see where they want you to stop. 0.5 divided by 0.5 is 1. And I have x equal to ln of 5 over 0.5. Okay, so that would be our final solution, but remember, sometimes my math lab likes us to stop a little bit early to try and kind of check and see if we know what we're up to. Okay, let's look at another one. Let's go ahead and look at log base 3 of x plus 4 equals 2. Okay, so in order to solve this one, I want to put this in exponential form. So 3 is my base, so I have 3 squared equals x plus 4. And now we're back to familiar territory. I'm going to flip this around so the variable's on the left. 3 squared is 9, of course. Subtract 4 from both sides, and I get x equal 5. So somewhere along the way, they might ask you to stop at this point, but you should always be able to double check these. Now, I'm going to graph this. And I would either graph log base 3 of x plus 4 minus 2 equals 0, because I'd have to subtract the 2 across, or I would graph the log conversion. Log of x plus 4 over log of 3. 3 is in the bottom, so it's my base. Now notice this minus 2 is not part of the arguments of the log here. So if you have a log base key, you'll use the top. If you don't have the log base key, you'll use the bottom. So let's go ahead and graph this one. So log of x plus 4 over log of 3. I'll just use that base conversion formula on the bottom. Clear both of these out. So I have log of x plus 4 divided by log, where's my log, of 3. Okay, now I have all those, and now I subtract my 2 and let's hit graph. Okay, so it's definitely crossing. It looks like right in here somewhere. It's kind of hard to tell. Let's go ahead and look at our second table to see if we can find out where that value is. And remember, we're looking for, these errors mean I can't take the log of a negative number down here. If I plug in a -3, however, I don't get a negative number back. I want to look to see where this changes from negative to positive, or gives me, oh, there it is. There's my 0 right there. So my solution here is 5. So that's really helpful. So let's go ahead and look at the graph again and the table. So let's pull that graph in and the table. And then we'll also do one other thing. In fact, I think I'll pull a different table or a different graph in than this, but we'll have that one for now. Second table. So we found our solution here is 5, which is what we thought it was as well from our work that we did by hand. So it's nice to be able to double check these. Now the table is giving this as an answer because it's a nice integer value. But the question is, what if it doesn't give integer values? What would we do? Well, if you look right here, this is where our solution is. The integer value shows, but what if it didn't? Well, you can go back in and use a second calc function, and what we want to do is choose 0, which is the second option, because I want to know where it's crossing. So basically I want to be somewhere to the left of where it crosses, and I'm definitely to the left of where it crosses. And then I want to move this cursor over until I'm somewhere to the right of where it crosses. And I want to make sure I'm to the right. There, I'm above. And then it says to guess, and if you want to, you can move the cursor over to where you think it crosses, but it's not a big deal. And it says, oh, your 0 is at 5. So this tells me, let's say my value had been a decimal or something similar, this would have told me what the decimal was, so I could have checked my answers. Because it's giving me an exact graph here, an exact integer value, I don't have to worry about it because the table gives that. But what if it wasn't showing up on the table? What would I do? So let's go ahead and put this in where I actually use that 0 function on your calculator to verify your answer. So all this work later, what we have figured out is we were right. 5 is my answer. That's where it's crossing. So this is saying the same thing. This is saying my solution is right here as well. So x equal 5. So you can graph a lot of these in order to check your work, and I really encourage you to do that. Let's go ahead and look at some other examples. Some of these won't be problems I can actually solve for right away or check on my calculator, but there are some handwork that I can do to get started. So this one would be a rewrite. This is log base 2 of x plus log base 2 of x plus 6 equals 2. Well, I don't have to do anything to this to solve it. I don't have to rewrite it. I could just put this in my calculator with my conversion if I need to, subtract 2, make sure it's set equal to 0. Or if I wanted to, I could rewrite these using properties of logs. So if you notice, this is the sum of the logs. Well, the sum of the logs comes from the log of the product. So this would be x times the quantity x plus 6 equals 2. So I'd have log base 2 of x squared plus 6x, because I would take the x and distribute it to both terms. And so now, rewriting in exponential form, my base is 2, my exponent is 2, 2 squared equals x squared plus 6x. So I have x squared plus 6x equal 4. I'd subtract the 4 from both sides. I have x squared plus 6x minus 4 equals 0. Now, this one's not going to give us a nice answer because this doesn't factor nicely. So let's go ahead and pop this in the quadratic formula. A is 1, B is 6, C is negative 4. X is equal to negative 6 plus or minus 6 squared minus 4 times 1 times negative 4 all over 2 times 1. Okay, so when we're using the quadratic formula, I'm going to move this over here. So I have x equal negative 6 plus or minus 6 squared is 36. Minus a negative is the same as a positive 16. That's my radical there, all over 2. Now I can't cancel the 2 into the negative 6 yet. 36 plus 6, that would be 36, 46, 52, all over 2. This simplifies into root 4, root 13, because 4 times 13 is 52. Square root of 4 is 2. And now I can think about canceling that. So I'm going to factor a 2 out of the numerator, and I'll be left with negative 3 plus or minus the square root of 13 all over 2. So I have two solutions, negative 3 minus the square root of 13, and negative 3 plus the square root of 13. Okay, so those are my solutions here. Now, a lot of times my math lab is good with you to stop at this point. They just want you to simplify and combine. Sometimes they want you to go through and solve. So let's go ahead and look at these on our calculator as well. This is log base 2 of x. To kind of remember what we were doing here. So log base 2 of x plus log base 2 of x plus 6 equals 2. That was my original problem. So I could go ahead and subtract over right away that 2. Now notice it's not within the argument of any of these logs. And then I could graph log of x over log of 2. Now if you have the log base key, you don't need to use these log conversions. Log of x plus 6 over log of 2 minus 2 equals 0. So this is what I want to go through and graph. Log of x over log of 2. So I hit y equal. So I have the log of x divided by the log of 2. And that was a plus. And then the rest of the problem I've forgotten already. Log of x plus 6 over log of 2. Log of x plus 6 over log of 2. And then we had to subtract that 2 over from here as well, so minus 2. Let's hit graph. Now, none of these solutions are going to show up on my table because with my table, what ended up happening is it only gave me integer values. Now, this is only showing me one solution, so that's kind of strange. We came up with 2. I wonder what's going on there. Well, let's figure out what that solution is. So we'd go to second calc, and I'd choose my second option for finding the 0 of that function. So left bound, let's see if we can, yep, there it is. So I had to move over a little bit. So left bound, and then right bound, and then go ahead and guess, and it's what, 1.0, I'm sorry, my solution is 0.605555128. So only one solution. I wonder what's going on there. If there's only one solution, that tells me that one of my solutions that I found by hand must be wrong. So let's go ahead and compare this to what we found. And then I think I want to look at some decimal approximations too of what we have going on here. So let's do -3 minus the square root of 13. So -3 minus the square root of 13 and -3 plus the square root of 13. So -3 minus the square root of 13. And then let's also look at -3 plus the square root of 13. Let's pull both of those in. Now one of those looks kind of familiar. So what's going on here? We can see that this one matches perfectly with this one. So that tells me that my solution here is the -3 plus the square root of 13. Why do I have to throw out this one? Why is this one not a solution? Well, the reason it's not a solution is this is a negative number, and I can't take the log of a negative number. So if I plug in a -6.6055, I can't take log base 2 of that number. You cannot take the log of a negative number. So not a solution. You cannot take the log of a negative number. Okay? Now, just because it's negative doesn't make it bad. What ends up happening is when I plug it in, I get back a negative number. So I could plug in a negative number and then end up taking the log of a positive number because I might add something to it. So it's really important that you think about not just the number is negative, but when I plug it in, the results are negative. So my solution here then is just the one, -3 plus the square root of 13. So I think for these problems it might be really helpful to graph them right away, and after you graph them you get an idea of what your solutions are. Now that one is a pretty complicated problem. Some of them might be a little bit easier, but graphing will always come in handy. So let's go ahead and look at a couple. 3 to the x equal 9. Now we already know my answer here is x equal 2 because 3 to the second equal 9. But I could graph this just to check it, and it's a good habit to get into even if it's an obvious solution. So let's go ahead and look at my y equal, and here I'd graph 3 to the exponent of x, and then I'd have to subtract the 9 over, -9 because it has to be set equal to 0, and we could graph it, and it should cross at 2. Better hurry up if it's going to. Whoops, there it went. It did cross. So 3 to the x equals 9. I can see that from what I have here that verifies to get x equal 2. And I know we knew our answer before, but when our problems get a little bit more complicated, it will be nice to have the knowledge of checking these to verify what our solutions are. So that's kind of why we did what's for an easier problem. Now if you weren't sure where this was crossing and you think it might have been crossing at a decimal, you could use the second calc and the 0 feature. So this is our solution, x equal 2. Now another way that we could have solved this is by taking the natural log of both sides. Now the whole reason for taking the natural log of both sides is to pop that x out front. So I'd have x times the ln of 3 equals the ln of 9. And then to solve both sides for x, I would divide both sides through by ln of 3. Now remember that you can't cancel the 3 into the 9. But ln of 3 over ln of 3 is 1. And over here I have the ln of 9 over the ln of 3. And let's go ahead and plug that in and see what we get. ln of 9 over ln of 3. ln of 9 divided by ln of 3. Now, one important thing to remember here is we have found this answer several different ways, and so when we're working through problems, you'll want to choose the way that's easiest. This one we probably didn't need to do so much work on because the answer was so obvious, but on some problems when the answer isn't as obvious, you'll want to be able to have these tools to use to check that answer. So again, this is equal to 2. So we found out our answer is equal to 2 like about 10 different ways. So again, a lot of the problems that we're looking at, there's several different ways to solve them. If you'd like to solve them a different way than I am, that's fine as long as you get the correct answer. So So let's go ahead and look at 7 to the 2x minus 1 equals 343. Well, if you realize that 343 and 7 have a special kind of connection there, it turns out that 7 to the third, let's go ahead and check this, is 343. So if you wanted to and you recognize that this was 7 to the third, then I can just equate my exponents. I get 2x minus 1 equals 3. I would add the 1 to both sides. I'd get 2x equal 4. Divide both sides through by 2. I'd get x equal 2. And if I wanted to check, 2 times 2 is 4, 4 minus 1 is 3, 7 to the third is 343. That would be one way I could solve this. However, if you don't see that connection between the 7 and the 343, what I can do is take the natural log of both sides. And you could also do the common log. For some reason, I just like to take the natural logs. So we take the natural log of both sides. Now the reason we do that is so we can pop these variables out front. So I have 2x minus 1, all of that, so I need to make sure I have parentheses, times the ln of 7 equals the ln of 343. Okay, so to get going here, we could divide both sides through by the ln of 7. Again, there's a lot of different ways to work from here. And I have 2x minus 1 equals the ln of 343 over the ln of 7. So to continue, we'd add 1 to both sides. And I have 2x equals ln of 343, ln of 7 plus 1, and then our final step would be divide through by 2. So I get x equal the ln of 343 divided by the ln of 7. So I guess that's a 7. It doesn't look like 1, so let's fix that. Plus 1, and then all of this is over 2. So this is interesting. Let's see what this turns out to be. We have to be really careful about where we put our parentheses on this problem, because without the parentheses in the right place, we'll get the wrong answer. So we had the ln of 343. So I want to make sure we open up some parentheses here. Ln of 343 divided by the ln of 7. Okay, and then we had a plus 1. Let me double check here. Yep, plus 1. And all of this is in my numerator, so I close my parenthesis then, and all of this is divided through by 2. Now my answer better be 2, because that's what we already figured out from another method. So 2 is my solution here, but man, that was kind of a long way around to get a number 2 out of this problem. So here, like I said, we get x equal 2 this way as well. So there's another way to do the problem, kind of a long way around the barn on that one. Let's go ahead and look at this in terms of graphing as well. So same problem, let's go ahead and graph this. So when we graph this, we'd go 7 to the 2x minus 1 and subtract over the 343. Now notice the 343 is not in the exponent, it's in the base. So let's say y equal 7 exponent. If you're using your exponent key and it just shows up as a caret, make sure that you have all of your exponent in parentheses, minus 343. Let's hit graph. Okay, let's see where this is going to come in. It should cross right here. Oh, yep, it did, right at x equal 2. So x equal 2 is definitely my solution. Not much to say about that, it's crossing it too. So graphing this is a very quick way to check your answers as well. Not a very exciting graph. It's just a constant. So we can see here that we have x equal 2 for my solution as well. So we've looked at several different methods for solving these, and again, like I said, pick the method that you want to use, and then based on that method, go ahead and solve. Now a lot of times we'll be looking for exact answers, and exact answers are just like I've said. They involve a fraction, they involve a radical, but they don't usually involve decimals. Usually what they want you to do is to find a solution first in exact form and then find a decimal form. Let's look at an example where we have 10 to the x equals 3.82. Now there's a lot of different ways to work this problem. I want to graph it right away. I want to have an idea what's going on here. So let's graph 10 to the x minus 3.82. Now notice the 3.82 is not in the exponent. So 10 to the x minus 3.82. Okay, so let's go to second calc. I want to find the 0 of that function, so it's going to graph it for me. Okay, my solution is somewhere between 0 and 1. It's not an integer. So I'm probably going to have to find an exact value and then compare my answer. So it tells me here that my answer should be about 0.582. So let's see what we can do to work with this by hand to find that solution. So I think graphing these is a good idea because I know right now I'm looking for one solution and one solution only. I'm not looking for more than one solution. Okay, so I already know my answer, but they want an exact answer. This is a decimal approximation. So since this is log base 10, what I could do is I could take the log of both sides. Now the reason I would take the log of both sides instead of the natural log is the fact that my base is 10. Because the log of 10 is just 1 then. So we take the log of both sides. Now the whole idea behind taking the log then is to pull that x out front, and I have x log 10 equals log of 3.82. The log of 10 is 1, and if you don't know that, that's fine. If you didn't know that, you could just divide both sides through by log of 10. And I end up with x equal log 3.82 over log of 10. Now if you wanted to do the ln instead, you could. It's not going to change your answer. You're going to get the exact same answer as you would get as if you took the log or the natural log. Sometimes in the directions it'll say, what is your solution in terms of natural logs? So if they say use natural logs, you do the exact same process, except you would use natural logs. So this would be the ln of 3.82 over the ln of 10. So you just need to make sure you read the directions to see what they're coming up with. So if they say find the problem in terms of natural log, that would be your answer. And then let's go ahead and jump into our calculator. That's the natural log of 3.82. Close parentheses, divided by natural log of 10. Okay, that looks familiar, so I hope that we have a solution here that matches the one that we found with graphing. Let's pop it in and see if they compare. So this is that 0.58206333, etc. It matches perfectly. So if they ask us to round this to 2 decimal places, let's say rounded, make sure you read the directions on rounding. So our rounded answer would be 0.58 if they wanted us to round it to 2 places. So this is our exact answer in terms of logs. This is our exact answer in terms of common logs. So natural logs, common logs, directions will tell you which one, and then our rounded solution. Now sometimes with some of these problems you have to do some work ahead of time, some prep work. So here we have e to the 4x minus 3 minus 7 equals 23,108. That's quite a solution. Before we can take the natural log or anything else of both sides, I need to isolate the base here. I need to isolate the exponent. So I'm going to add 7 to both sides. And I have e to the 4x minus 3 equals 23,115. And then I'd solve from here. I'd use whatever method, you know, I could take the natural log of both sides, I could graph. So there's a couple different things we can do here. I'm going to take the natural log because again we have the log base e. I could graph this as well, but when you graph it, it's only a good time to check your answer because they always want your answer in exact form. So this would be 23,115. The whole idea of taking the natural log of both sides is to pop that exponent out top, out front. And I have natural log of e. And I have the natural log of 23,115. Now I'm trying to solve for 4x minus 3. If you can recognize that the natural log of e is 1, that's going to make this a lot easier. So I have the natural log of 23,115. So I'm going to add 3 to both sides. And I have 4x equals natural log of 23,115 plus 3. It's not in the argument of the log. And then, of course, divided through by 4. So I get x equals the natural log of 23,115 plus 3 is not part of the argument of the log over 4. So this is our exact form. And then, of course, if I wanted to plug this into my calculator to get a decimal form, I could. So exact form and decimal form are both going to be important here. Now, one thing that we haven't touched on is how to graph and solve log equations. We've mentioned this briefly, but I want to do a couple more of these before the end of the lecture. So this is log base 5 of x plus 4 equals 2. Well, if I wanted to graph this, this would be log base 5 of x plus 4, and I'd have to subtract the 2 across to set it equal to 0. And if I didn't have my log base key on my calculator, this would be the same as graphing the log of x plus 4 over the log of 5 minus 2 equals 0. So let's go ahead and think about graphing either one of these and coming up with a solution. I'll go ahead and graph the one with the log key, just because we haven't done that one lately. So if you have the log key, you'd go under Math and then either scroll up or down until you got to the log base key. And if you don't have a log base key, you'll graph the other option, the log conversion. So this is log base 5 of x plus 4. Now outside of the argument, then, I would subtract 2. And we're trying to find our graph. Now, looks like it's crossing way out here, so I think I'm going to have to change my window. Let's go ahead and go up to positive, let's say 40, just to make sure we get it covered. So it's crossing, this is 40. Looks like it's crossing halfway between 0 and 40, so maybe around 20. So I could do my second calc and look at option 2 to find the 0 of the function. So I think it's crossing in between right around 20, so I want to make sure I'm well on either side of 20, because it's hard to tell when it's skimming the x-axis like that. And so 21, it's crossing at 21, so we were pretty close with our guess of 20. So we know our solution here is 21, and since it's an integer, that's an exact value. So there's really not a lot of handwork I have to do on this one to solve, but I'll show you how to solve it by hand as well. So I know my answer is 21. So this is my solution. So my answer is x equal 21. Now if I wanted to solve this by hand, remember I started with log base 5 of x plus 4 equals 2. I rewrite this in exponential form. My base is 5, so I get 5 squared equals x plus 4. So I have x plus 4 equals 25. Subtract 4 from both sides, and you can see I have x equal 21. Now when you plug that back in, I don't have a negative number here, so that's nice. I don't have to throw out that solution. So these are other ways that I can use to check or to graph a lot of these equations. Now sometimes when I graph them, I'm going to get a decimal, and so I have to do the handwork. I don't have a choice. I can't just rely on the graph. Let's go ahead and look at another one. 9 ln of 2x equals 45. Same directions as before. I need to isolate. Last time it was the exponent. I think this time we'll just isolate the log, and then I can start working the problem. So I have the ln of 2x, 45 divided by 9 is 5. Now let's think about what natural log is. That's log base e of 2x equals 5. So this would be e to the 5th equals 2x. Divide both sides through by 2 to solve for x. I get x equals e to the 5th over 2 as my solution. E to the 5th over 2 for my solution. So I could check that if I wanted to by plugging it back in. So let's go ahead and check that. That's not anything that we've done too much of today. So I have 2, and then e to the 5th over 2 and I'm checking to see, does this equal 45? Well, these 2's cancel, and I have 9 ln of e to the 5th. Does this equal 45? The 5 pops out front, so I have 5 times 9 ln of e equals 45. Checking to see if that's true. You can plug this directly in your calculator, unless you know that ln of e is 1, then this makes it pretty easy. And I get 45 equals 45 for my solution here. Or not for my solution, but to verify my solution. My solution is e to the 5th over 2. So again, a lot of different ways to work these problems. I could have also graphed this to come up with my decimal approximation, but I definitely have to do the handwork on these first. So when you're simplifying, you know, make sure that you're being very careful about your numbers. Make sure you plug them back in, because not everything has a solution. Best thing to do first is to graph these to see if you have, you know, 0, 1, 2 solutions, and then work on your handwork to see if you can verify those solutions, and then check it again using the second calc and then the 0 function. If you have any questions, please make sure you bring them to class. Stop by my office hours, or you're always welcome to step into the MAC as well with any questions. Good luck.